So, hi everyone. So thank you for attending this live presentation. So my name is Tin. I'm a security analyst at Ishard. I mostly do reverse engineering. And today I'm with my colleague Pierre-François. Can you please introduce yourself a bit?
Yeah. Can you hear me?
Yep.
Yeah. So to introduce quickly myself, so I'm Pierre-François Maillard. I'm also security analyst at Ishard, and I'm also customer success. So I'm taking care about clients and technical communications. And today's purpose is to introduce time travel debugging and most interesting how it's possible to combine time travel debugging and AI, which is right now one of the most interesting features that will come within the ES Reverse platform. But not only, I think, in the world right now, and that overcome most of the limitations that we have right now with the debugger and AI when we want to perform an analysis.
Yeah. So the topic today is time travel debugging, and more specifically, how TTD changes the way we investigate software behavior and why it becomes even more interesting when it is combined with AI agents. So basically, the idea is simple. When you debugging usually means observing a program while it runs. But with TTD, we record the execution and then we can come back to it, replay it, and move backward, inspect it again, and ask new questions after the fact. So instead of saying, can we reproduce the bug, we can start saying, can we explore what already happened? And that difference is very important. So maybe you can start by giving a basic definition when we say TTD here. What exactly do we mean by TTD?
Yeah, I think always the best thing is not to only give negation, is to show the things. Uh, Basically, when I am with a debugger, I'm working at one particular context, and at this particular context, I will be with my debugger, be able to look into memory and everything. And in this particular context, debugger is quite useful. The problem being, very often you want to go back in the execution and to explore, okay, what was this memory space at this particular time and what it will be in the future and things like that. And with a debugger, you can't do such things. You need to restart every time your execution, every time that you want to see what happened. And between every execution, like the memory can change and things can change. And the concept of time travel debugging is quite simple. I will take, let's say, one process and record everything that happened during all of the execution of this process. So let's give an example right now. I don't know if you see my screen.
Yep.
Yeah, okay,
Can
perfect.
you maybe collapse the
Yeah,
sign?
yeah, it will be better. Yeah. So in this particular context, I am, for example, is one particular, I am in one particular process, and within this process, I'm able to see all of the. I don't know if you have some noise from your side, Tim. Yeah. In this particular process, I'm able to see all of the instruction, like during the execution, but also all of the memory space that are associated at instructions. And to perform analysis is, I want to say, maybe the best way because you have always access to everything. You can't go further than that. Like, and you can see what happened maybe 1 million instruction after and 1 million instruction before. And when perform analysis is very, very powerful. Um, I want to say it's the next evolution after a debugger. I don't know what to think about that, but mm, we can't do more than that because everything is recorded. The specificity that we have at the time travel debugging of each chart is the fact that instead of recording one particular process, we record the entire operating system. And the main advantage being whatever you have within the operating system will be able to save it to analyze it after. So it's quite powerful. So in this particular interface that I have there, for example, I have approximately 79 million of instructions. And within this 79 instruction, I'm able to navigate within it to see at any point of time what happened. And we can have way more features than just a debugger. For example, if I take one particular memory space, wherever it is within the program, I'm able to see exactly when it has been read or write all over the times. So let's give an example tomorrow. I have a key somewhere, and I want to know who have written this particular key and when this particular key is read in the future. I just jump directly in this particular memory space, and I'm able to see exactly what happened, who wrote it, who overwrite it, who read it, and in 1 second, I'm able to do such things. While for a debugger, it will be necessary for me to put a watch point and follow the executions, and sometimes I need to break point at the particular moment where it will be interesting and things like that. So that's why right now, time travel debugging, I want to say, is very, very powerful. But from my point of view, it has only one main limitation. It's not straightforward. And that's the main problem right now of time travel debugging, the fact that it's a huge quantity of informations. And analyzing all of this quantity of information requires very advanced skill, way more advanced than a debugger, for instance, because you need to be able to find exactly in these 79 instructions where is a particular point that you want. Yeah. You're mute, I think. I don't know if you try to talk.
Yeah, you are talking about full system recording, but I just wanted to mention that we also manage single process recording. So we keep enough execution state to debug the past execution, almost as if it were still alive. So that is what makes it different from traditional tracing, login, or crash dumps, like you already mentioned earlier. And uh, can you explain the difference between recording a single process and recording a whole system for on our platform?
Yeah, like I mean, different way depending also on the way that you have to record it. For example, on Android, if I remember well, for you, you will be able to use FreeDA to record one particular process on the phone or directly on a virtual machine. We have also some solution when you can perform some emulations through Chilling or Unicorn. On this particular case, you can emulate only one process and be able to analyze only this particular process. In general, it's, I won't say surprisingly easier to record the complete virtual machine. Why? Because virtual machines, you just start your virtual machine, say, I want to start my record, execute, let's say, a malware, finish, say, okay, no, my record is finished, I will be able to analyze it after. But when it is a process, you need to understand, okay, the process will start at this particular point until this point, or you need to be able to emulate it. But both of them serve different cases. Uh, when you analyze a complete virtual machine, the problem will come after. When you will have finished to do the recording, you will have this maybe 1 billion of instruction to analyze. When you analyze a process, it will be very less, maybe 1 million, few hundred thousands. So it will be way easier in that way. So both of them serve different purpose.
Yeah, yeah, I agree with that. And just to give another example, a concrete example also, if when we talk about single process recording, we can also have in mind WinDBG, WinDBG TTD, which is free and built into Windows. But it only records a single user mode process. So if a malware drops a driver or an exploit crosses from userland into the kernel, WinDBG cannot see what happens next. So you can only capture the trigger, not the full story. So that is exactly the gap that full system recording addresses. You mentioned the example on Android, for instance. We can record an entire emulated device, all the kernel operations, all the processes that are spawning, network communications, and so on. And but of course, if we record too much, we also need better ways to navigate the trace. And that's where our current graphical user interface helps you with, and also the Python API that we provide in order to navigate and analyze this very huge data.
Yeah.
So yeah, but
When we're
yeah.
yeah, when we're talking about WinDBGTD, there is another very well-known limitation, the fact that you can analyze only one process, and this process need to be a ring tree. So in fact, in most of the exploitation, ring zero will come into the game, and you can't record even the ring zero process. So for this reason, like WinDBG have been created to be a debugger, not to analyze vulnerability, where time travel debugging in full system is designed purposely to analyze vulnerabilities.
Mm. Right. And if you look at the interface that you are sharing right now, uh, so let's not look at just the interface only as a set of panels. You can view it as a workflow. And there's one thing to understand first. So this is not a disassembler and it is not a decompiler. For a beginner that starts using the graphical interface and that is used to tools like IDA and Ghidra and so on, it can be a bit confusing if you read the code top-down like you would in a normal debugger. And this way you can miss the point. So here the interface is memory-centric, and you start on a point of interest, a string in memory, a memory structure or a function call. And then you ask the trace where it came from and where it goes. So that's basically if I would resume the workflow for when using our graphical user interface. But that brings us to the one problem, which is that okay, TTD gives us a lot of power, but it also gives us a lot of information, maybe too much information sometimes. And unfortunately, humans do not scale very well when the search space becomes too large. And this is where I think we need to be honest when TTD does not magically solve analysis. It just gives us a better ground truth. It gives us replayability and observability. But someone still needs to ask the right questions. Like someone still has to decide where should I look, which function matters, which memory write is relevant, and so on. So when the trace is large, it becomes difficult, not because the information is missing, but because there's too much of it. So when you analyze a trace manually, uh, uh, why do you think you usually lose time uh, to your experience?
Like you said, when I analyze the trace manually, the main question is where should I start? When I have, I don't know, 80 million of instructions, I'm like, okay, it's nice, I have everything, but where should I start? Where should I look into? So at beginning, you will look basic thing like where are the strings? If you have something relevant, or okay, maybe I would look for one particular memory space or something like that. But very fast, it become a huge amount of information, and it require a lot and a lot of skills. That's the main problem of time travel debugging, not the fact that it is uh, like an impossible solution, just the fact that you need to be an expert to be able to analyze everything, and it requires a lot of time of analyzing. So from industry point of view, it requires to have very advanced people to perform such analysis. And in general, for me, when I start, like I said, I struggle to find the entry point. Once you have the entry point, you just follow the line, so it's way easier in that way. But just starting to find it is a struggle, definitely. And that's where I think AI came into the game a lot. Why? Because if we struggle to analyze 80 million of instructions, which is something I want to say quite difficult, it's very simple, I want to say, for AI to analyze such quantity of data in a very, very short time. And in the past months, like we have performed a lot of research and tests on how it's possible to integrate AI within yes, reverse solution, and especially time travel debugging on full system. And I guess we got quite good result regarding it. We have created an also an MCP solution to be able to interconnect this trace of 80 million of instructions with like one your AI that will analyze this 80 million of instructions. And it has a lot and a lot of advantage, I want to say. First of all, the main problem right now that we see when we perform analysis with AI is the fact that it's very difficult to perform dynamic analysis. The debugger have a problem of lack of context, and as I was saying, AI does not perform that well with the debugger. But in the context of time travel debugging, the concept is I will take my dynamic execution and I will record everything to convert it into something that I can analyze in a static way. Because this trace at the end is just a static analysis in a different form. But just I take my dynamic, I convert it into static. And static things are very, very easy to analyze for AI. We see that with all of the, like if you try to use, I don't know, the MCP of Guidewire, you will see that you will have very, very good results until dynamic execution come into the games. So in that
Yeah,
particular, yeah,
yeah, yeah. Go on, go on, go on.
yeah, in that particular way, that's our main point of focus right now is how it's possible to develop as much AI as possible to simplify the analysis traces. So the only limitation that was having time travel debugging was the fact that you need a lot of training and expert to analyze it disappear because no AI can assist someone to find exactly the particular instructions, the particular memory that you need to focus on, and after that you can perform your own analysis following that. Even you can have automatic analysis through AI of time travel debugging.
Yeah. So, so yeah, right now the AI agent can query the trace. It can inspect execution state. It can follow events, and it can ask for more context. And that is quite important because runtime analysis is interactive by nature, and you rarely know the answer from the first question. You start with hypothesis, you test it, you refine it, and sometimes you abandon it. And that loop is exactly where agents are, in my opinion, interesting. So this is part of a broader shift that we are seeing across reverse engineering. The community is moving from simple prompt-based help, where a human asks one question at a time, toward agentic workflows where the system wields tools autonomously, decompilers, debugger, tracers, and so on. And so that's structured workflows that turn shallow exploration into much more useful analysis. So let's move from the concept to the actual workflow. Uh, can you show us how does the TTD AI workflow start?
Yeah. In fact, I don't know if you have said it at the beginning of the stream, but you can have access to a set of traces directly on tte.ishar.com. It's a set of traces that are pre-made, so you can only have access to this limited set, but you can perform your own analysis of time travel debugging through these traces. And they are completely free, no subscription, and you can directly have access to it. So when you have one, you will have the graphic interface that I talked just about, and you can do manual analysis on it. But if you want to test AI, it's possible to directly test it even right now, and you don't need to pay anything for that. You just need to have access to this platform and to have an large language model right now to test it. So there we have an MCP, which is you can directly connect, which is hosted within our environment, but you can directly connect to directly see how it's possible to solve this particular challenge. So this trace is a challenge. You need to submit flag there through the AI agent. So for that, I will just add this particular MCP within my environment. Start Cloud, for example. And then let's say I will take, which model will I take? Default model will take Opus. And I just have to say after that, okay, no, please solve my challenge. And we don't give more information about that. The MCP is not fine-tuned specifically to solve this particular challenge. Just we have created an MCP where the purpose is to solve any possible challenge that will come into the game, and we apply it to a set of different challenge. And then you can see how it performs and how it performs the analysis. So even for people that want to perform the manual analysis, they will be able to see how AI can have their way to analyze a particular traces that can be useful because they do it quite fast. And people that want to come into the game of AI, that is right now the future of reverse engineering, you can directly see why time travel debugging is beating using a debugger when AI come into the game. So right
Yeah,
now,
in this example, it's a CTF challenge, so it will trigger a specific workflow related to CTF. But you also have workflows for exploit if your use case is exploitation, and many more workflows will come depending on the use cases that we want the MCP to handle. Uh, so
yes,
yeah, just another information also. Here the CTF is angry pangolin. So if you want to try it, just add the MCP. And at some point, if you want to look at the solution, there's a blog post on our website that covers the solution that that was solved by an AI agent actually, and we wrote a blog post with the solution. So yeah, play with it on our platform ttd.tshare.com if you want to, and if you want the solution, it's already published.
so maybe to give you an estimation, generally this challenge, like in practice, when we go to conference, we are giving this challenge to people, and I want to say 50% of people were able to solve it, 50% were not. And within these people, in general, they take, let's say, 3, 4 hours. The fastest people take less than 1 hour, but in general, let's say 2 hours in average. And let's compare with right now with how fast the AI agent is able to solve it. It's exactly the same thread that we are giving in the past months in conferences, and we can see that it go quite fast. And by itself, it's able already to excuse me to inspect some particular transition, particular address, and get all of the data which is necessary. And you will see that it's quite powerful and even surprising, because sometimes the workflow that AI agent have is not the one that we were thinking it will have, and even then is able to get the things that we want. And something which is even more surprising is the fact that this MCP server that we have right now created is not finalized, I want to say. There are many features that the MCP server, like the Cloud Agent that is using right now, is not using because we didn't finish to develop it. But some of these features, for instance, are the access to the symbols. Right now, the agent does not have access to any symbols, so it's just working within 80 million of instructions without having any information about which function he is in or not. It does not have access to what else? To one of our main feature, which is the tent analysis that help you to jump from one particular, like to follow the one particular value within the execution flow and things like that. And even then, without all of these features that are, I want to say, core feature for analysis, is able to solve most of the challenge. And not only challenge when we use it to debug some like some execution to verify where is the vulnerability of something. In less than 30 minutes, most of the time, you're able to find the root of the cause without even all of this feature. So yeah,
Yep.
the can you repeat it, yes, please, Sandra? Like the yeah, it will be easier. I can't hear you properly.
Can
Can
you
you
cut the cloud.json file in the current
in the current folder?
session?
Oh, yeah, yeah, we'll be able to solve it after. Yeah, yeah, I can cut it. I just make it execute it just before, to make it test before the sync, but in any case, I can cut it just after if you want, no problem for that. And, from your side also, if you want to test it, like I want to say you can also test it from your side. If you want to be convinced about it, you can directly use the AI on it. At the end of the execution, I will cut it. And, you can even test it by yourself to verify that it works directly, even without any, information before, I want to say.
So if I just summarize what you just said previously, so right now it's not finished yet. It's not a finished magical system. So there are still limits, as you mentioned. We still need to add more good tools. The agent needs more context also. A trace alone is not always enough. As is mentioned, it may need symbols, function names, memory maps, or domain knowledge. And one very, I think, important information is that the agent can follow a wrong hypothesis. That's and that is not tied to our MCP or uh, it's more a defect from the agent, the model that is used. But this is very important because an agent may find an explanation that looks plausible, but that does not mean it has explored all alternatives. So that is why the human analyst remains important because he defines the question, he reviews the reasoning, and he has to check whether the conclusion is strong enough or not. So the goal is not autonomy for the sake of autonomy. The goal is just to provide uh, another alternative, a new tool for a better investigation when dealing with a huge TTD trace.
Yeah,
Um,
yeah, I just check right now, does this work for Android apps on kernel? Um, right, I think
yeah,
this version is working already on Android, traces, this
yeah,
part.
it's yeah. We basically the trace format is the same. It's just obviously not the same architecture. But right now, with the provided tools inside the MCP, it's already works quite well for Android traces. And yeah, maybe in the future we will add more traces instead of just Windows related traces. We will add Android traces or even IoT related traces because we can also leverage Unicorn to emulate a code and generate a TTD trace for that emulated code. And with that, uh, we can also provide this kind of trace also. And of course, we also handle Linux platform. So yeah, maybe in the future, we will upload more traces for you to play with on the platform.
Yeah, right now, like I said, it's a limited set of traces. We only have Windows right now, but it's not a limitation of the MCP, just a limitation of the things that are shared within the platform. And yeah, we'll be able to do searching from adding new architecture is not something difficult for that. So right now we have the solution of the challenge. We can see directly. Solution is star is shard star.
Okay,
I'm sorry
we
for
just
the.
yeah we just spoiled the, the flag. Okay.
Yeah, yeah, but it's okay. Like the purpose is for demo reason. This I think this you didn't share it on the blog post, the flag?
Ah
No.
no, I removed it.
Okay, so no, it is shared within the live demo, so it's okay. No problem for that. So it was some modification that were performed on two process, one on the user land and one driver. Uh, so just one typical example of why it can be used, but it can use in many different other topics, like I said, uh, crash analysis or whatever it is. In parallel, like the interface that you have seen there, that was quite, I want to say, old, have been completely changed and come with a new one that is way better, way more modern, and give you the possibility to develop some feature. And what will be interesting is the fact also that this interface have right now the same limitation that the AI agent have, because we don't have all of the functionalities that we have on the old one. The functionality will come soon. And it's quite interesting to see, like, to see this one, because we see that from human point of view, analyzing that can be, I want to say, a nightmare, but from AI agent point of view, it has been something quite simple. So to have this point of view is also quite nice. And in the future, this interface will be the new one and will be the future one, like the only one for future. And one other interesting part also come is the fact that right now we use MCP mostly for analyzing traces, but to perform a traces, we have also the record part, or it's possible to record it. When we record, let's say, I want to see the execution of a driver, like some part of the execution of a driver. At this point, I need to do it manually. That can take times also. And for this reason, right now, we plan to also create another MCP that will help the people to analyze it, like to perform the record assisted by AI. The purpose at the end, I won't say in the best way, AI will do everything and will do nothing, but I won't say in most of the cases, it will be necessary also to have a human that can at least have a control on it to verify that everything go well. And so we can have a workflow. We can imagine in future where you will just, let's put a particular binary. The binary will be executed on one particular environment. The record will be performed directly, automatically. You will have the record with you, and the MCP will directly analyze it. And then in future, you will can combine the analysis of the MCP of time travel debugging with the MCP of, let's say, IDA, Ghidra, whatever it is, to have the best of both worlds, the dynamic analysis and the static analysis.
I also wanted to add something else. If you can come back, please, to the action GUI.
To, yeah.
Yeah. So, can you show us the frame buffer, please? Uh,
I don't have it there. I think so. Yeah.
yeah, so as you can see, the graphical user interface, so we record almost everything and the frame buffer also. And what's interesting here is that, so a concrete example to illustrate this is just have a look at the blog post that we have published regarding the on-grip pangolin CTF. But what I wanted to mention here is that because we have the frame buffer, we also gave eyes to the MCP. So it's interesting to look at the session that you run with when the AI agent runs from a single prompt, like solve this CTF challenge. And most of the time it goes for some low level hanging fruit, like strings, symbols, and so on, but also the frame buffers. And by getting those low hanging fruits, it can go from there to go backwards and then find the root cause of something. And right now, the free primitives that TTD gives to the agent is memory access tracing. So the agent can ask, for instance, who wrote this value to this address and when. So a single query, and the answer points directly to the next step in the chain. And if you apply it forwards, it can be who reads from this address after this point, and then it follows the input bytes through the entire transformation. The agent just follows the data, does not need to deduce the data flow from static code. There is a second primitive that we provide, and that is used a lot by the agent is virtual to physical address translation. In the example, in the Angry Pangolin CTF, in this example, there's an accumulator that was accessed at one virtual address in user mode and a different address in kernel mode. And here the agent asked the trace, do these two virtual addresses map to the same physical page? And for this example, the answer is yes. And in one query, the agent resolved an, an ambiguity that would require a kernel debugger, a manual CR3 lookup, context switching with traditional tools, and so on. So uh, more tedious than using one single trace that records everything. And lastly, the third primitive that is used a lot by the agent is the, as I mentioned at the very beginning, is the frame buffer, because the trace includes screen snapshots at any execution point in time. It reads the frame buffer at the very first context. It sees what was uh, displayed on the screens, if there is any test input, any failure message. So from there, it does not do any guessing about what the program does. No disassembling printf calls, just the actual screen output. So actually, here the agent starts from observation and not from speculation. So these primitives are not magic. They change the unit of work for both the analyst and the agent. And when you run the agent and you want to verify something, of course, you still have the graphical user interface to jump anywhere you want in time to verify if what it says makes sense. And as I said at the very beginning, you also have a Python API if you want to do more analysis if you are limited by the graphical user interface. But yeah, right now, I think with the MCP agent, well, so far, I think it's more powerful compared to the API Python. At least for now, I didn't meet any concrete use cases where I needed to go back to the Python API. Uh, yeah.
Uh,
So,
Something
yeah.
quite interesting is the fact also that AI agents sometimes request some features that are not there. Uh, I have a few example in my mind, but like some features that can be easily there within the time travel debugging like interface that we have there. It said, "Oh, if I would have that, it would be quite helpful for me for my analysis." And it's not there yet. It's easy for us to add, but because it is not there, he's not able to use it. So we are right now also working on developing these features that will help the AI agent, but also the manual analysis, both of them. So the AI agent help us also to develop new feature. Definitely, it's quite nice in that way. So I was thinking, for example, I mentioned previously we have the right now the memory history within the interface. When I have when I have an interface, I take any memory space, I'm able to see when this particular memory space is read or write or overwrite all over the time. Okay, it's a bad example because this thing is only write. But if I take, for example, this one completely randomly, this one is read or write over the times. So like the AI agent use it a lot. But this thing is developed for memory, but AI agent said us, okay, but I want to have exactly the same feature with a register, for instance. And right now we are, for which reason is it really useful? Yes, no, maybe. At least you want to see when it is overwrite and when it is used to be read. And so we have developed the same feature. For us, it's quite simple to do because the way that the memory is moving and the way of register are moving from our point of view, it's quite the same. But from the AI agent, it will help him to go even further on form analysis. This new feature will be very useful because AI agent says that it is very, very useful. So it's one example, but many other will come to speed all of the analysis. Okay.
Yeah,
So
so I think we can conclude. I don't know if you what you think.
yeah, I think we can.
Yes. So
So yeah, do you want to okay, you want to
yeah, I
conclude?
just yeah, you can add if you have anything else to say. But yeah, to conclude, I think the important idea is that TTD should not only be seen as a manual debugging feature. It can be become part of a larger automated workflow. Imagine that interesting executions are recorded automatically, a crash or suspicious behavior, malware execution, or I don't know, a fuzzing case. So instead of keeping only logs or only a crash jump, we keep an execution trace. Then an analyst can, or an AI agent can come later and investigate what happened. So to me, that changes the role of debugging, where debugging becomes less about catching the moment live and more about exploring recorded behavior afterward. Uh, so I think that we already see this in this pattern in practice. On Android, the the common workflow that I have is prepare the application, log into it, try to go through some runtime checks if I need to by using Frida. We save the VM snapshot just before the action that I want to record, and then we record only the target interaction, and then we generate the trace. So this snapshot ensures that the trace stays focused, and the analyst or the agent comes later to rewind to any point and inspect what actually happened. So there is no reproduction, there's no need to rerun anything. So I think the main message is TTD gives us replayable execution, and AI agents gives us scalable exploration. And together, it can create a new way to investigate complex software behavior, not by replacing the analyst, but by giving the analyst a much more powerful investigation loop.
Yeah, for my side, I think something which is quite important is like reverse engineering is changing completely. We have seen it. It's not a surprise for anyone that AI coming really into the games, and the fact that in the pack we are using mostly, let's say, the assembler and the debugger together. We were using a debugger because it was compared to time travel debugging easier. On time travel debugging was quite difficult and too much information to analyze. But what was true maybe a few months ago is not true anymore because right now this large amount of information is not a disadvantage, it's even an advantage right now because we have more information to analyze. So for AI, it's way easier to go directly to the solutions. So right now, uh, AI will change a lot of things in reverse engineering, and time travel debugging is maybe one of the main things that will come into the game for all of this analysis. So if you want to try it directly, you can go on tt.ishard.com. You can directly use it with your own model if you want, and try to solve the challenge. You will see that it go quite fast for the 3 challenges that are directly within it. And we will add also some other traces. We are talking about Android previously. It can be quite interesting for people to be able to analyze such things. So, okay, that's all I think for this live. If you have any question, feel free to contact us directly on our website, and we'll answer to it. No problem for that. Okay,
Yeah. So thanks
thank you very
everyone
much.
for attending. Thank you, Pierre-François, and see you next time.